Okay. There are still people coming. Okay, now that. Okay, I think let me sorry, start the recording. Okay, I think that the number is sort of reaching a steady state. So good afternoon, everyone. Welcome to this edition of the NITheP webinar. This afternoon, we are very happy to have Dr. Nina Megier with us. She's originally from Poland, but she studied in Germany. Walter Strunz was her master's and PhD supervisor, if I remember correctly. And since probably a year or so, she's an Alexander von Humboldt Fellow at University of Milan and is working with Bassano Vacchini, that some of you might know because you visited us in Durban, I think once or twice. Yeah. So Nina, we are very happy to have you with us this afternoon. And we are very much looking forward to your talk on local and non-local master equations. And if you would like to share your screen, you're welcome to do so and to start your presentation now. Thank you very much. And sorry, while you do that, I always forget to mention that participants are welcome to ask questions in the Q&A facility at the bottom, and Ilya, that you see at the top on the panel, will moderate the questions after the talk. Fantastic. Now we can see your talk. So Nina, thank you. Over to you.
So firstly, thank you very much for giving me this opportunity to give this webinar. So the work was done not only with Bassano Vacchini, but also with Dr Smirne. And yes. So to start the talk, master equations are used to describe the evolution of open quantum systems. So the defining property of open system is its coupling to some external degrees of freedom. And because in praxis this coupling is almost never negligible, the theory of open quantum system is relevant in many different parts of physics. By way of illustration, for example, in quantum optics, where in cavity quantum electrodynamics one investigated an interaction of atoms with a light confined in a reflective cavity, or even in biophysics, where one assumes that also quantum properties play a role in high efficiency of photosynthesis. So if we have open quantum systems, then of course, in principle, one could describe it as a closed system, but it is in practice too difficult because too many degrees of freedom in the environment. So I'll try to reduce the description. And the object one mostly then investigates is reduced density operator. So the reduced density operator is obtained from total density operator by tracing out the environmental degrees of freedom. And this is a relevant object because actually it described all information about the reduced system. In a sense that for all local observables A of the reduced system, the expectation value of this observable can be obtained only with knowledge of this reduced density operator. Okay, so the goal now is to obtain the evolution equation for this reduced density operator, which is mostly called master equation. So the path one can go is to start with this total dynamics. Then we know that the whole system is covered, the evolution of the whole system is covered by von Neumann equation. And then simply tracing out the environmental degrees of freedom on the both sides. So on the left-hand side, one obtains the derivative of the reduced density operator. On the right-hand side, of course, in general, one will not get the same structure as in von Neumann equation with the reduced system quantity. So this would be the case if the reduced system would be closed. So in general, one gets some functional of the reduced density operator. And this functional can have two forms. So the first one is the time non-local. So that means that the functional depends on the whole history of this reduced density operator. So here I assume that in the initial time of the evolution, so the evolution starts at t equals 0, and I also assume throughout my presentation that the system and the environment are initially factorized. So that means that at t equals 0, there is no correlation between the system and the environment. And because of it, this functional is linear, and that's why one can indeed write this as this convolution I have written here. Okay, so this is the first type of master equation, which is time non-local. There exists also time local master equations, so where this functional depends only on reduced density operator at a current time t. And one could think that the second type of master equation is much more rare, and mostly one encounter this time non-local master equation, but this is actually only partially true. So under assumption, quite weak assumption on the dynamical map. So dynamical map is a map which takes the reduced density operator at initial time at t equals 0 and map in on the reduced density operator at time t. So conduct this time evolution. And under an assumption that this dynamical map is invertible, one can show that there then indeed this time local master equation always exists. So I can obtain it from time non-local master equation by writing the rho s at time s as rho s at time t, then evolve it back to initial time t equals 0, and then evolve it again to time s as I marked here. And then this object in red now, the whole object will be the generator of the time local master equation. But actually this condition is not necessary. This is a sufficient condition. So there are also some other situations where this time local description exists. So in the following, I will simply assume it is the case. So one have both time non-local master equation in principle and also time local. And when it is the case, then both descriptions are in principle equivalent, because they give us the same information about the dynamics. So actually they give us the whole information about the reduced dynamics, because they give us simply the reduced density operator if we solve it, then of course. Nonetheless, it can be of advantage to know both. For example, because one of them can give us easier access to some properties of the dynamics, or one of them can give us better understanding of the physical origin of the dynamics. And here I will give, for each case, I will give one example. So for the easier access to some properties of the dynamics, I give an example of time local master equation, and in the case of the better understanding of the physical origin of the dynamics, I give time non-local one, but this assignment is not fixed. So in other situations, it can be other way around. Now we investigate this case of easier access to some properties of the reduced dynamics, and the property I will be talking about is quantum non-Markovianity. So this is generalization of classical Markov property. So firstly, I will roughly say more or less what the Markov property is. So this is a property of classical stochastic process, and roughly speaking, to give a feeling what's going on here, so Markov process is process for which the future does not depend on its past. So for example, if I have some coins and I put them in a bag, and then my process consists of throwing the coin and then put it back in a bag, and I make it many times. And at some point I ask a question, okay, which coin I will throw now? Then for this process, the knowledge of the history of the drawing is not relevant. So it will not be beneficial for me to know the history. So this process is memoryless. But if I change the setup and after drawing the coin, I will put it in my pocket and not in a bag, then the knowledge of the history would be beneficial for me. So for example, in this particular example, I will know that in the third drawing, I will get €1 coin. And otherwise, I will have to assume that the probability is 50-50 to get €2 and €1. So this process has a memory. And the dynamic of open system can be seen as stochastic process because we do not have access to this environmental degrees of freedom. This is also the case in classical, for classical system. Most known and enlightening example is Brownian motion. So Brownian motion describes, for example, a motion of pollen grains on the water surface resulting from its collision with the water molecules. And of course, so here in this picture on this video, there's this yellow dot is pollen grain, and this gray dots are water molecules. So of course, if we know the whole system, so this movement of this pollen grain is deterministic. But because we cannot observe these water molecules, the movement of this pollen grain seems to be for us stochastic. So what we see is simply a single realization of the stochastic process, which we would then describe in terms of mostly Liouville equation. But we could also describe equivalently the evolution of the probability density with something like Fokker-Planck equation, and in quantum physics it would simply correspond to the evolution of the reduced density operator. And going back to this Markov property, so in the classical case, it is clearly defined what the Markov property is in terms of endpoint probability distribution. And however, the transit to the quantum regime is not straightforward because of the disruptive character of the quantum measurement. So in quantum physics, there exist many different definitions of quantum non-Markovianity, which are not equivalent, but to not take into account this quantum measurement, Mostly they are described in terms of the properties of a master equation. So the equation for the reduced density operator. Okay, so we are now here. So we are talking about this local and non-local master equation. I have said that it is of advantage to know both because of two reasons. Now we are dealing with time local. We will be dealing with time local master equation from which it's easier to see quantum non-Markovianity. And the master equation I have written here, firstly, it's time local because only on this dependency on the current time t on the right hand side. This equation, this master equation, is mostly known under the name of generalized Lindblad master equation or generalized GKSL master equation, and generalized because these decay rates they can be time dependent, and the sign of this decay rate is connected with quantum non-Markovianity, or to be more exact, with a property called Cpt divisibility. So Cpt divisibility, this is a property of dynamical map. So lambda of t, which takes again initial density operator, reduced density operator at time t0 to density operator at time t, at a later time t. And this dynamics can be divided in two steps. Firstly, I evolve my reduced density operator till some time s, which is smaller than t, and then take this reduced density operator and evolve it from time s till time t. The problem is, or the thing is, that this object, this lambda ts, which takes the reduced density operator at time s and evolve it to time t, in general, it does not have the same properties than the original map. So it does not have to be CP, which means complete positive, or actually it even doesn't have to be positive. But here we focus on Cp divisibility. So if this lambda ts is Cp for all t and for all s, then the dynamical map, the evolution, is called Cp divisible. And this can be seen from the sign of this decay rate. So if all of the decay rates stay for all time non-negative, then the dynamic is Cp divisible. If it's not the case, then it is not Cp divisible. So only looking at this form of the master equation, of the time local master equation, one can read out this property without knowing the dynamical map. Okay, now we are going to the case where the time non-local master equation can be beneficial. And in this case, it will help us to better understand of the physical origin of the dynamic. And we show it on an example of quantum semi-Markov dynamics. And here I have shown dynamical map. To show you more or less what these quantum semi-Markov dynamics are. So this is again generalization of classical concept. Now I will describe the particular trajectory or the single realization of this reduced dynamic. So firstly, I start with some initial state rho s at t equals 0, which is the same for all trajectories. Then I evolve it, continuously evolve it till random time t1. And this evolution takes place in terms of map F, I have marked, and this randomness is governed by this probability density Pn, which give me the probability density for n jumps at fixed times, t1, t2, and so on. So now I have reached this time, random time t1, and I jump. And the jump is given with this map epsilon, which is in quantum physics, then for the quantum semi-Markov dynamics, is it Cpt, so complete positive, ray preserving map. So a proper quantum evolution. Then again, I evolve with some random time t2, I again jump, and so on. So this is quantum semi-Markov dynamics. And if I additionally assume that this continuous time evolution between jumps is not there, so in a sense, this F operator's identity, so nothing happens between the jumps, then the time non-local master equation corresponding to this quantum semi-Markov dynamics looks like this. So we have this dependency of this jump map epsilon, and the function key under the integral, it's memory kernel. So firstly, this is time non-local master equation, depends on the whole history of the evolution. And the nice thing here is that by having this master equation of this form, I know that underlying dynamic can be at least interpreted in this way I have shown you in terms of this jump process. Okay, so we have shown that it can be of advantage to know both forms of the master equation. So our goal is to find a connection between local and non-local master equation. And one of such a connection we have already seen. So in a moment in which I have explained, okay, if the dynamical map is invertible, I can get from this time non-local master equation to time local one. The problem with this is that I have to know this. I have to know dynamical map, and not only this, I have to know the inverse of the dynamical map. So this is mostly not given, so I will try to find another connection. And firstly, we can look how these generators, local generator and non-local generator, how it's connected with the dynamical map, and then derive the connection between the local and non-local master equation. So for the local generator, this connection can be derived and it looks like this. For the time non-local one, one can write one connection in time domain. That's the first one. The second one is given in the Laplace domain, so where this the tilde there denotes the Laplace transform. And from these connections, one can derive the connection between time non-local and time local generator, given here, again in Laplace domain. The problem here is that, again, I have to know at least the dynamical map, because on the right-hand side, I have always product between the time non-local generator and the dynamical map. And again, this is mostly not given. So one want to go beyond this. And the path we went was using damping basis decomposition. And how to get to damping basis. So if we have linear map psi acting on some set of linear operators denoted here, linear operators on a Hilbert space, denoted here with rho. Then we can take some orthonormal basis in this Hilbert space with respect to the Hilbert-Schmidt scalar product. So this orthogonality is given here with trace operation. And then we can always write this Xi map in this basis in the following form I've marked here. So decompose this map in terms of this basis, and this matrix M in this decomposition, it's in general non-Hermitian and it's also non-diagonalizable. So if it's not diagonalizable, then okay, one can bring it in nonetheless in Jordan form. So here we have this decomposition in Jordan form. So on the diagonal, we have the eigenvalues, the corresponding eigenvalues, and if for some eigenvalue the algebraic multiplicity is larger than 1, then we also have 1 on the minor, on the corresponding minor diagonal. But here we have assumed, okay, I assume that this matrix M, that our map is diagonalizable. And this makes the story much more easier. So then we have such a form of the decomposition, which is called in terms of damping basis. So this zeta and tau in this decomposition are B-orthogonal. That means that they fulfill such a equation. So the zeta and tau corresponds, like to say, to the left and right eigenvectors, and they are in general different because this map M I have shown previously was not Hermitian in general. If it's Hermitian, then the zeta and tau are the same, these are the same basis. If not, then the left and right eigenvectors differ. Okay, and then we also can do this linear map Xi time dependent. So in this case, two things can happen. So the first thing can happen is that this eigenvalue will get time dependence. So will start to be time dependent, and it can both happen. This eigenvector zeta and tau, eigenoperator zeta and tau, it can be time dependent. However, if we assume that the linear map is commutative, that means that for all t and s, this property I have marked is fulfilled, then in this case, this operational part will stay constant, so it will not be time dependent. Only the eigenvalue will get the time dependency. And we play this game for a dynamical map. Okay, sorry. So dynamical map, we assume that the dynamics is commutative, that it is diagonalizable, and under this assumption, we get this decomposition or this representation in terms of damping basis, where the only time dependency is in this functional part. So m alpha of t, small m alpha of t, they are functions of time, and this cursive m alpha, capital M alpha, this is this operational part, so or even super operational part. And then if it's the case, then the same is true for the local generator, and not only this, so not only the same structure is given for the local generator, also this operational part is the same. So it's not only for both, in both cases, time independent, but it is the same. And what is more, even for this non-local master equation, the same can be also said. So this non-local time, so time generator of the time non-local master equation has the same structure with the same time independent operational part. So here again, once more for the illustration, we have dynamical map lambda, generator, time local generator, time non-local generator. Both have the same structure with the same operational part. The only difference is with this functional part, which is time dependent, and what's more, one can also explicitly write the connection between this functional part. So here the connection between the functional part of the local, of the dynamical map and the local generator is given here for the time non-local generator and time local one, where this curly I denotes inverse Laplace transform. So in general, it cannot be conducted analytically, but at least one can explicitly write the connection. So we have found accordingly this connection between local and non-local description for commutative diagonalizable dynamics. We have seen that even if these both descriptions are equivalent, it can be of advantage to know both. For example, because one of it can give us easier access to some properties of the dynamics. We have seen this on example of time local Lindblad equation, so Lindblad equation and the property of quantum non-Markovianity. Or the other reason can be to better understand the physical origin of the dynamics. We have seen this on an example of time non-local master equation, which describe quantum semi-Markov dynamics. But now I would like also to show you different application of this damping basis approach for Redfield-like approximation. And the Redfield-like approximation of the reduced dynamics is done in the following manner. So we have the exact reduced dynamic, and if this non-local generator K of t is significantly different from zero only on time scale much shorter than the relaxation time of open system dynamics, then in this case I can simply take out this reduced density operator out of the integral, set it to be at time equals t, and then the time local equation I obtain will have the time local generator of a following form. So it's simply the time integral over this non-local generator. And one can show that in this damping basis approach, that this time local, this approximated time local generator has exactly the same properties as the exact time local and exact time non-local one. So one can see that not only the exact time local generator and exact time non-local generator has the same operational, time independent operational part, the terms, but also the approximated approximated time local generator. So this red field time local generator, and one can also write the connection between this time non-local functional part and red field functional part, which is written here. Okay, and now the stamping bases also help us to investigate some properties of this red field, like approximated dynamics. So the first example of this will be in terms of quantum semi-Markov dynamics. So of this type given by this equation. So once more, when this continuous time evolution is not there, so nothing happens between the jumps, I have said that then the master equation, time non-local master equation, looks like this. And okay, and with this equation, we conduct the Redfield-like approximation. So we approximate the dynamics in the following manner, and time-dependent prefactor in this approximated local dynamics is this function S of t. And this is actually a function which is called renewal density, or also sprinkling distribution. And from the property of the memory kernel, one knows that it is always positive function. And because this form of this local approximated local master equation is Lindblad-like, is of this generalized Lindblad form, we conclude from this, okay, that the approximated dynamics is Cp divisible, so it is Markov according to this definition. So no matter what the original dynamics was, so the only thing is that it has to be of this quantum semi-Markov type given here, we know that the approximated dynamics is Markov, is Cp divisible. An example of this original evolution is if the jump channel is given in this manner. So this operation performs a diagonalization in the eigenbasis of sigma z. And then starting with the exact non-local master equation, we derive exact local master equation, and we look at this side of this prefactor, we look at this prefactor in this Lindblad form of the master equation, and we see, or we derive that this is actually a function called the hazard rate. So the hazard rate is given in terms of waiting time distribution and survival probability. So this hazard rate h of t equals f over g. And because both this function, both waiting time distribution and survival probability, they are positive function, the hazard rate is also a positive function. So we can conclude that in this case, the original dynamics was Cp divisible, and the approximated dynamics was Cp divisible. So the Cp divisibility was conserved. But this is not always the case. So the other example of this original dynamic is if this jump map is given in this form. So this where sigma, sorry, I didn't mention this, the sigma here are Pauli matrices. I hope it was clear from the context. So, so this operation performed the phasing operation, and then the corresponding exact time local master equation it is also of this Lindblad form. It has a different prefactor, and this prefactor, this function, in this case, can get negative. It can even diverge. So this is completely different type of the dynamics. So in this case, the original dynamic was non-Markovian, non-Cp divisible, and the approximated dynamics is Cp divisible. So one can also see the difference looking on between these dynamics, looking on the evolution of the coherences in the basis of sigma c. So on the y-axis, we have this function c of t, which describes this evolution of these coherences, and the different color of these lines correspond to different weighting time distribution, so different memory kernels. Here I have chosen Erlang distribution, so this weighting time distribution obtained by considering the convolution of n exponential distribution with the same rate parameter var epsilon. So that means for this parameter n equals 1, which is called shape parameter, we have simply an exponential distribution, so the most Markovian one. And for higher n, one has the convolution of this exponential distribution, so some more complicated, classically non-Markovian one. And we see that, so the solid lines correspond to diagonalizing dynamics, which was Markov, according to our definition. The phasing one, so the dotted lines correspond to the phasing one, which was non-Markov. So one see that all solid lines, they are monotone, so monotonously decrease of the C of T, of the coherences. In the case of the phasing dynamics, only for n equals 1, only for exponential distribution, the function monotonously decrease. Otherwise, we get some revivals or even reborns of these coherences, which is a signature of non-Markovianity. Okay, so we have seen that by this Redfield-like approximation, one can go from the Markov dynamics or non-Markov dynamics and get Markov dynamics. So in a sense, the approximated dynamics was more Markov. Generally, it's not the case. So with our damping basis approach, one can derive some general statement, at least for some classes of dynamics. So for example, if here I have written the formula, general formula from the local generator, if it contains only a single eigenvalue, so this only for a single alpha, so the sum is running. So there is only a single term in the sum, to put it so in this case, the Cp divisibility property will be conserved. So that means if we start with the original dynamics, is Cp divisible? Sorry, I forgotten to write this. If the original dynamics is Cp divisible, then the approximated dynamics will be also Cp divisible. In a more general situation of Pauli channels, which are also commutative and diagonalizable, so we can use our machinery here, one can show that the P divisibility is conserved. So when this map lambda Ts, it's not Cp, it's not complete positive, but positive. So this then this property is conserved, but not Cp divisibility in general. So one can start with a Cp divisible map and approximate the dynamic, and what one gets, the approximated evolution is not Cp divisible. So in this sense, P divisibility is more robust. And I would like to show you an example of this phenomena. So this is qubit dephasing in random direction. So firstly, when the direction is fixed, the master equation, time local master equation looks like this, where the sigma alpha are given by scalar product of this direction vector n, normalized direction vector n, and the sigma vector consisting of sigma 1, so sigma x on the first place, then sigma y, and so on. So this is the dynamic when the direction of the dephasing is fixed. If we allow the direction of the dephasing to be random with some probability distribution, then the dynamics would look like this. So we have some sum, like say over this 3 direction, but this function gamma k, it depends. So it's time dependent, first thing. Second thing, like to say, it depends. Each gamma k depend on all probability of the direction. So it's depend on the parameters x1, x2, and x3, when xk give a probability, or is given in terms of the average second order correlation for this direction vector. So in a sense, it gives a probability that the dephasing occur in this direction. And from this, from the fact that this vector is normalized, this n vector is normalized, one can conclude, okay, this x1 plus x2 plus x3 equals 1. So it can really be seen as this probability of dephasing in one of the direction. And if we look at the property of the Markov property of the original dynamics, so in terms of Cp divisibility, so for all choice of this parameter x1, x2, x3, the dynamics is always p divisible. The Cp divisibility property is a little bit more complicated. So this is this cube on the axis, we have this parameter x1, x2, and x3. And because we have this constraint that the sum of it is 1, the choice of the possible parameter is restricted to this yellow triangle I have shown. And each color, so area of each color corresponds to different time in which all of this decay rate are positive. That means that if all of the decay rate are positive, the dynamic, at least till this time, is Cp divisible. So initially all choices of, so this is the yellow area, all possible choices of x1, x2, and x3 give us Cp divisible dynamics. For later times, we see that some choices of these parameters, which are near to the border of this triangle, will lead us after some time to non-Markovian dynamics. So at least actually in this case, exactly one of the gamma will turn negative. And when the time evolves, this area or this set of possible choices for which the dynamic stays Markov it gets smaller and smaller, but at the end it approaches this star-shaped area, which is denoted with the black color. So if I choose these parameters x1, x2, and x3 in this black region, then the dynamics is really Cp divisible. That means for all times, all of the gammas stay positive or 0. And now I will look at the approximated dynamics. So I take this exact time local master equation, then derive the time non-local master equation and do the Redfield-like approximation. And the dynamics I obtain, or the non-Markovianity of the dynamics I obtain, is given with this feature. So where the meaning of the scholars is the same. So we see that also initially all of the gammas are positive. When the time evolves, this amount of choices of parameters which lead us to the Markov dynamics will get smaller and smaller. But in this case, this area, if we get the time evolve, if we evolve the time, this area which give us real Cp divisible dynamics, so for all times, all of the gammas are non-negative, is only this tripod configurations consisting of 3 lines. So it's much smaller. So that means that the original dynamics is more Markovian than the approximated one. And one could also look at these properties, general properties we have derived from this damping basis approach. So for example, that P divisibility in this case, because this system falls onto the set of Pauli channel, so the P divisibility should be conserved, and this is of course the case as it should be. Cp divisibility, as I have shown, it's not in general, but one can also ask, okay, if one only have single eigenvalues, the Cp divisibility should be conserved. And in general, we don't have only single eigenvalue for this system, but for particular choices of this parameter x1, x2, x3 we have. And these choices are choices given with these dots, black dots. So the dot in the middle is not visible because there everything is black, but these are the one dot is in the middle of the triangle and 3 dots on the tips. So these are the dots which correspond to choice of these parameters x, which give us a dynamics with only single eigenvalue in our damping basis decomposition. And we see that in the approximated dynamics, indeed, the Cp divisibility, this property of Cp divisibility is conserved. So in this case, if the dynamics was originally Cp, it stays Cp divisible, so it stays Markovian. Okay, I would like to summarize my talk. So I have shown you that master equation can be of this time local and time non-local type. And even if they are equivalent, if both of them exist, the knowledge of both can be beneficial. For example, for knowledge of some properties of the dynamics, I have shown it on example of quantum non-Markovianity, or to understand the physical origin of the dynamics, I have shown this in terms of quantum semi-Markov dynamics. For commutative diagonalizable dynamics, I have given a simple, easy connection between this local and non-local generators, and I have also showed the application of this damping basis decomposition to see some properties of the Redfield-like approximated dynamics. Okay, so thank you very much for your attention.
Yeah, Nina, thank you so much for a very nice talk, a fantastic overview of local and non-local dynamics for master equation, and some very interesting recent results that were actually the reason why we asked you to give us a talk. So thank you very much for sharing that with us in some detail. Now it's time for some questions. Ilya, are there any questions, or is anyone of the participants wanting to ask the question? Just please raise your hand and we can give you the rights to speak.
Okay, so far there is none, but probably people need to digest it a second. And meanwhile, can I please ask a question? So
you go ahead.
You've shown a very nice transitions, you know, when you have some kind of exact master equation and it's, for example, Markov, and when it's approximate, it's non-Markov, but it's all on the level of the master equation. Are you aware of microscopic derivations which can tell you like what kind of physical systems you need to take such that, or which kind of system bus interactions, which correlation functions, such that one can obtain such a transition? Thank you.
From Markov to non-Markov, or?
No, but I mean, like, whatever, like, I mean, Markov from non-Markov, non-Markov to Markov. So like when you have some kind of, you know, when you write a master equation, it's a nice mathematical formulation. And of course, you know, I understand that in principle, physical systems should exist. But, you know, if I would like to propose to someone to do an experiment, we need to know what kind of physical system one should have in mind, which kind of correlation functions we need, or which type of interaction between system and bus. Do you have any ideas about that?
So I think to say in general what property of this dynamics will lead to going from the original Markov dynamics to non-original, to approximated non-Markov one and other way around. I think the general property is not known. And this is a little bit similar, I think, from the spirit of the fact that mixing Markov dynamics can lead to non-Markov one, or other way around. So I'm not aware of any specific property of the dynamics which make it more existent, like to say. So I don't think that it's so easy to answer this question.
Okay, thank you. And we've got a question from anonymous attendee, so I assume that implies that the person do not want to ask it in person. So let me read it. Hi, can you comment on the dimension of the underlying Hilbert spaces? Are the dimensions of the density operators derived from the master equation restricted to being countable, or could they be acting on uncountably infinite Hilbert space?
So we have done this in for finite dimensions. If there are some finities, mathematical finities, which will make the situation more complicated in this non-finite case, probably, yes, maybe, I don't know. But everything we have done, we have assumed, okay, we have finite Hilbert space, we have finite dimension.
Okay, thank you. Okay, so there is a Camille who wants to ask. Let me allow him to talk.
Yeah, hello, Lina. Thank you for this nice talk. It's more like a comment than a question. So this process of like averaging, to take the approximation of the map reminds me a little bit of what one of our colleague is doing, Vinayak. I don't know if he was listening to the talk, but so Vinayak was looking at the problem of when you add a dynamical map, and so it gets this like let's say counterintuitive result that if you add a Markovian map, you can end up having a non-Markovian map, which is a bit, not very intuitive, because one would say, if you have no memory, you had two maps with as no memory, you should get no memory at the end. But in some case, you get some non-Markovian map. And I think I have the same feeling with this approximation of the map. I would say, if you have a map, you get the approximation. You should, at least if the map was initially Markovian, you should get the approximated map should be Markovian. And and you show in some cases, it's not true. You start from a Markovian, you get the approximation, it's non-Markovian. So I have the same feeling of surprise, I would say. And I wonder if there might be any connection. I don't know the details, if there might be, but something else is that the picture you show of the region of parameter are very similar to the ones that Vinayak shows. So, I don't know if there might be any connection or not, but So
okay,
do you know?
Maybe, maybe can you write me on, I don't know, email or on chat or whatsoever the publication or have paper or that I will.
Yeah, sure.
Thanks.
Yeah, and Vinayak is here, so I can see him. Yeah. Not really, but
okay.
Yeah.
Almost.
Yeah.
And I don't know if we have 1 or 2 more minutes. I would like also, I don't know, is there any more question? Otherwise, I would like to ask you if you could briefly come back to the damping basis. Just briefly explain the beginning, because at that time my connection failed, and so I didn't manage to hear what you were saying.
Probably this slide is.
Yeah, friend, just how you introduce just the beginning of this damping basis.
How I introduce, okay.
Yes,
so,
how you introduce it, yeah.
Yes, so to introduce it, firstly one have this linear map psi, and one choose some basis, some orthonormal basis with respect to this Hilbert-Schmidt scalar product. And then of course one can, like to say, decompose, write this map in terms of this basis. So then the composition looks like this. And this matrix M can be then diagonalized, which corresponds simply to changing the basis. Of course, in general, it cannot be diagonalized. We assume that it can be diagonalized. So the damping basis is simply the basis one obtains then by diagonalizing this matrix, but one have to, like to say, only not forget that this matrix is non-Hermitian in general. So that means that this left and right eigenvectors are different in this case. So this zeta and tau, they correspond, like to say, to left and right eigenvectors. And this lambda, this is some number, like to say, some eigenvalue. Okay. And then if one comes to time dependency, then in general, so make our linear map time dependent, and in general both the functional part, so this eigenvalue can be time dependent, but also this operational part, so this eigenvectors can get time dependency. But this is exactly not the case when this map is commutative. So that means it's commute for different times. And in this case, only the eigenvalue had the time dependency. And like to say, this is the key point then in our what follows, that only this, so that the operational parts at the end does not change, does not evolve, and only what we have to derive is actually this connection between these functions of time.
Okay, and so I have the feeling, and I guess this is why this basis is called the damping basis. So this basis give you the what sometimes people call the decoherence basis. So like it will give you the eigenbasis of the steady state, something like that, right? Or not necessarily? Or you're not sure?
I don't know.
Okay.
So
okay,
I don't
it's
know
fine.
what to say something
Okay.
stupid.
Okay, it's fine. I will check. Maybe. Okay, but thank you for answering my question.
Thank you for asking.
And Nina and Vinayak just posted in the chat the reference to the paper that Camille referred to.
Okay, thank you very much.
So, but we can email it to you. We can email you the PDF later. Yeah, no problem. And maybe we can discuss it separately because it might get a little bit technical and not so interesting for everybody. Yeah. Can I ask one last quick question? Ilya asked you about the microscopic derivation. I will ask you my other preferred standard questions. Can you unravel your semi-Markov processes in terms of the wave function somehow? Or up to what stage can you use your damping basis maybe to create some new interesting unraveling for non-Markovian dynamics?
So we didn't use it in this manner. So what I like to say generally know, of course, one can unravel it in terms of stochastic Schrödinger equation, which then would be non-Markovian. So the interpretation of them would be maybe problematic, but formally one can do this. But we didn't look at this by using this damping basis in this manner. So
okay, yes. Thank you. Just curiosity. Yeah. Okay, Ilya, if there are no more questions, I think
no.
No. Okay, thank you. Then,
no, there is a quick question from Vinayak.
Okay.
Could you please comment on what waiting time distributions is in the quantum case, unlike classical semi-Markov case?
Sorry, once more, I didn't get it.
Can you please comment on what waiting time distribution is in the quantum case, unlike a classical semi-Markov case?
So for the semi-Markov, I will say something, but I don't know if this answers your question. So for the semi-Markov dynamics, both classical and quantum, you can take waiting time distribution as you wish, which governs this process. So the only thing is that this function, this probability of n jumps at this fixed time t1, t2, and so on, that is connected with this damping, with this waiting time distribution in this manner. So with this G is the survival, corresponding survival probability, and F is waiting time distribution. And it can be taken as you wish in both cases.
Okay, thank you very much, Nina. I'm sure that Vinagia will be in touch also for the other issues. So maybe you can discuss it in a different setting. You know, it's almost 3:15, and you know, people probably need to leave now. So I would like to thank you very much for the very nice presentation. You saw from the number of questions that people are interested and will probably continue the discussion with you after the webinar. So Nina, thank you very much again. We will post your talk on YouTube just now, and we will share the link with you. And it would be really very nice to stay in touch for the future. So all the best to you and your team. Thank you very much. Have a good afternoon. Yeah,
Bye.
thank you. Thank you very much.